Okay, we're going to talk about graphing in kinematics today. And this is an area that we went over last year, and we did spend a lot of time on it, but we're going to spend even more time on it this year because graphing is something that a lot of people will avoid initially. They don't like questions with graphs, but it is crucial that you understand how graphs work and that you start to build that understanding early on in this course. We're going to see a lot of similar things to what we saw last year. We'll also see some more complex graphs, and you're going to be expected to be more fluent with these graphs this year. So what graphing boils down to, really there's two calculations I have to make, and I want to go over those calculations first. The first is a slope calculation. You've probably been doing slope calculations since at least probably about 5th grade or so. And you can tell me, and you remember from last year, that the formula for the slope of a line is as follows. The slope is equal to y2 minus y1 over x2 minus x1, where the 2 and the 1 just represent certain coordinates that would be on the line that you're trying to find the slope of. Okay, now what a lot of people do, well, what a lot of people tell me if I ask them, hey, what is the formula for the slope of a line, they will tell me this. They'll say, oh, it's y equals mx plus b. And it makes sense. I understand why they're telling me that. What they're thinking of, this equation is not the slope formula, that would be this one up here. This equation is instead what I like to call the general equation for a line. It is the equation that describes a line on some graph. Y equals mx plus b. Y and x are your coordinates, the x and y coordinates, like you would have on a graph. M is the slope, so that's why they think that this is the slope formula, even though it's not. And b is that thing called the y-intercept. It's where the line intercepts the y-axis, where it hits the vertical axis. Okay? Now, some other things that you need to know about the slope are the units. And this one can also be a stumbling block for people when I tell them, hey, what are the units of this line? They sometimes get a little confused. You don't have to memorize the units of any particular slope. It's always right there for you. If you're taking two y coordinates and subtracting them, and taking the two x coordinates and subtracting them, well, the y coordinates have units on them. Subtracting the two y coordinates is going to give you whatever the regular whatever the units of the y-axis are, since you're taking two y coordinates, and the same thing for the x. x2 minus x1 must be measured in units of whatever the x-axis, whatever the units are on the x-axis. So your units here are simply what I like to call the y units over the x units. It's nothing more complicated than that, okay? You don't have to memorize the units for all these different types of lines. All you have to do is look at what are the units on my y-axis, what are the units on my x-axis. Why do we measure slopes? Why do we care? The reason we care is that measuring a slope is useful for determining how the y variable changes due to changes in the x variable. And the reason that makes a lot of sense is because if you look at your equation for a line, you have y and x in here. If you have a certain value for x, and then you were to change that, that's going to influence the y variable. The whole reason we're making a graph is because we have two variables that are related. One variable influences the other. So the reason we measure the slope is we're trying to determine how this y variable will change because that x variable has already changed. We're trying to predict how those changes work. So that's the first thing that we look at, the first calculation that we make when we look at graphs. We also, as you might remember from last year, want to calculate the area under the curve on occasion, the area under the line or curve. And just as a review, you've been finding area probably since even longer than you've been finding slopes. The area formula for a rectangle is a equals base times height, or length times width, or whatever, doesn't really matter. They're the same thing. And the area formula for a triangle is a equals 1/2 times the base times the height. And the units of this are as follows. If you're measuring the base times the height of some shape that's being made on your graph, well, the base would be just measured along the x-axis, so that would have units of whatever the units on the x-axis are. And the same thing for the height. The height is measured along the y-axis. The units would be whatever the y units are. So the units here are simply the x units times the y units. And why do we care about the area? Why is it useful? And the answer is a little funny. It's only useful sometimes. And it's more similar to the slope than you might think. It is useful for determining how a quantity has changed over time. So the slope is kind of like finding out, okay, well, how much is whatever we're looking at changing right now? How much is the x variable changing, or y variable, excuse me, changing right now at this instant because of the x variable? The area is kind of like saying, okay, well, over this long time period, how much has this other variable been changing? How much has something been changing? Okay. Now we're going to look at a few different types of graphs, x versus t, v versus t, and first thing we're going to do is we're going to do those slope and area calculations, and then we're going to look at some other questions you might want to know, and we're going to use these slope and area calculations to kind of tease out what information you can get from these types of graphs. Okay, so we have an x versus t graph right here. Let's see, the first thing I want to do is calculate the slope, and in order to do that, I should draw my line of best fit. So I'm going to put my protractor down, my straight edge, and I'm just going to draw a line so that we have a line to look at. Okay, there we go. Now, first thing I want to do is calculate the slope. We know that slope is y2 minus y1 over x2 minus x1, and the points, point number 1, point number 2, have to be on the line. Okay, they have to be actually on the line that we drew. If they're not on the line, then we can't use them to find the slope because they're not on the line that we're trying to find the slope of. Let's see. So for this one, I'm gonna do this easily. I'm gonna take my last point and my first point. Let's see. The coordinates of the last point, that looks to be, let's see, y2 looks to be about 75 or so meters. y1, that looks to be about 5 meters. And x2, let's see, that would be 10 seconds minus 0 seconds. So we have 75 minus 5, that's obviously 70, divided by 10 minus 0 is 10. So I get a slope of 7. The units are going to be whatever the y units are, units on the y-axis, over the units on the x-axis. So that would be meters over seconds. Okay, I'm going to leave that for a second. We're going to go calculate the area. Remember, area under the curve is a little strange. I have this shape, what I'm looking at is this shape all under here between the x-axis and my line of best fit, line or curve of best fit. So I want to find this area here. It looks kind of like a triangle, but notice that it's actually got 4 sides. It's got this little tiny one here, 1, 2, 3, 4. So what I'm going to do is break this up into a rectangle and a triangle. And you can do this for any graph shape that you get in this class. You really don't need to know the area formula for a trapezoid. You don't need to know the area formula for anything else, really. All you need to know are the basic area formulas here. I mean, and these should be drilled into your head at this point. You might remember the area formula for a circle, but I can't see you needing that in this class for right now. So I'm going to break this up into a big triangle, a little tiny skinny rectangle down at the bottom. So we're going to draw that. I'm just going to put a dotted line here to make it a little easier for me to see. Okay, so for the area, let's do the area of the rectangle first. The area of the rectangle, the base of the rectangle goes from 0 to 10, so that's 10 seconds. So base times height equals 10 seconds. And the height, it goes up to about, let's see, about 5 meters. So that would be 50. And the units, again, are x units times the y units. That's 50 meters seconds. Meters times seconds. It's a weird unit. Okay, let's do area of a triangle. That's 1/2 base times height, which is 1/2. Let's see, the base is 0 to 10, so that's 10 seconds. And the height, it goes from 5 meters all the way up to 75 meters. And we know the difference between those two. It's not, the height of the triangle is not 75 meters. It's 75 meters minus 5 meters, because that's how much it goes down to, which is 70. So 70 meters. Let's see, 1/2 times 10 is 5. 5 times 70 would be 350. And again, the units are meter seconds, m times s. So if we want the total area, that would be area of the rectangle plus the area of the triangle, which is 50 meter seconds plus 350 meter seconds is 400 meter seconds. Okay? Now, so we found the slope, we found the area. Let's start talking about a little bit more about what this means. And before we do that, I'm going to get into kind of a little template for you that I think these are questions that you should always ask whenever you're faced with a graph, an unfamiliar graph, or any type of graph, to help you understand. You should make slope and area calculations, okay, especially if it's asked for you to do that. But you should also be asking yourself these three questions, just kind of get a gist for what is happening with this graph. Okay, so we're going to make a little section over here. These are the three questions to always ask about a graph. Question number one. Okay. Question number one is the y variable positive or negative? For this graph, this is an x versus t graph, so position versus time. You could also call it displacement versus time graph. A distance versus time graph is slightly different, but we're going to stick just for right now with displacement versus time, or position versus time, whatever you want to call it. Is the x variable positive or negative? So our answer to question number one, is the displacement positive or negative? Very clearly, all of these and so that's what the that's what the y coordinates are showing you. All of these y coordinates are positive. Okay, the y coordinate is the displacement. That means the displacement is positive the entire time. So the answer to question number one is the displacement, or position, you could say, is always positive here. Now, is it going to be like that for every x versus t graph? Absolutely not. But on this one, it is. It is always positive. And the way we know that is x is greater than 0. It's above the x-axis at all points. Question number two that you should always be asking, and there's two different ways that you can ask this. Is the y variable increasing or decreasing? Is the y variable going up or down? Is it increasing or decreasing? As you look at the trend, it's very obvious. The y variable starts at 5, 15, or no, 5, let's see, about 12, 19 or so. It's going up all the way to 75. Okay? So is the y variable increasing or decreasing? The y variable is increasing here. So that means the position is increasing. An equivalent way to ask this, if you think about it, is the following. Is the slope positive or negative? If you think about it, those two questions essentially mean the same thing. Is the y variable increasing or decreasing, or is the slope positive or negative? They will give you the same answer. The y variable here is increasing the whole time, and the slope is positive. Those two things are linked. The position is increasing, that's my symbol for increasing, and slope is, I'm not even going to put and, I'm going to just go put a slash. The slope is positive. Those two things are linked. They have to both be true for this particular type of graph. So notice that we did get our slope, a positive value for the slope up here, and let's look at the units of the slope, meters per second. What else has units of meters per second? Well, that would be velocity. Okay, so in this case, the slope is actually telling us, as you probably remember from last year, the average velocity. So I'm just going to add in here, slope of x versus t equals average velocity. Okay, very important fact to know. Displacement slash position is always going to be positive for this particular graph. So that essentially means what to do if you need to know where an object is for an x versus t graph. You just look at the y-axis. You look at the y-coordinates. And that's kind of a self-explanatory one. So I guess I'll write, anyways, to know position on x versus t, look at y coordinates. And I'm sorry, I'm squeezing that in here. Okay. So there's my first two questions that I always ask when I get a new graph. Let me put the third one down. The third question is the following. Is the value of the slope increasing or decreasing? In other words, is the slope getting more or less steep? Remember, last year when we first talked about slope, I told you the best way to describe a slope is to think of it as the steepness of the graph. If you think of it as the steepness of the graph, it makes a lot of sense. I'll zoom out just a little bit for you. Okay, sorry about that. So yeah, if you think about it as the steepness of the graph, that's what a slope is really telling you at the most fundamental level. So here, what I would say is this slope, if you look at it, it's the same steepness throughout. The slope is positive. Don't get positive mixed up with is the slope changing. It is a positive slope, but it is not a changing slope. The slope is not increasing or decreasing. It's not getting more or less steep. So I would say the slope is not getting more or less steep. Now remember that slope we just said was the average velocity. The slope equals the velocity. If the velocity, the slope, is not changing, if it's not getting more or less steep, then we could say it's constant. And if we therefore say that it's a constant velocity, then we know that if the velocity is not changing, the acceleration of whatever object this is must be 0. Okay? So I'm going to put in parentheses, slope is constant, so average velocity is constant, so the acceleration is 0. And remember that the units are meters per second squared on acceleration. Okay? So on a graph like this, to figure out the position at any point in time, you look at the y-coordinates. To figure out the velocity at any point in time, or the average velocity, you look at the slope. To figure out if it's accelerating or not, you look at how the slope changes. So, to describe acceleration on x versus t, look at steepness change of slope. Look to see if the steepness of the slope is changing. Okay? And so those are 3 facts that should help you when you're analyzing an x versus t graph. Now those facts aren't going to be the same for every graph that we look at, but for the most part, those are going to be pretty consistent. One other thing that I do want to point out is we did find the area here. We found the area under the graph was 400 meters seconds. You guys don't know anything that's a meter second. That's not a unit that is measured for anything really. So this is not useful to you. Okay, the area under a curve is actually meaningless for an x versus t graph. Okay, so we've got some facts here. Most important of which is probably the slope of x versus t is the velocity. You can tell the acceleration by looking to see if the slope changes at all and describing that change. And the area under the curve really isn't all that meaningful. When we come back, we're going to look at v versus t graphs, a v versus t graph, an a versus t graph, and then probably, hopefully, if we get there in time for the next video, practice looking at some other graphs. Okay? I'll see you in a bit.